All right, let's get right into it. We're going to be looking at what seems like a simple graph, but I want you to see it in a whole new light. This isn't just some line on a chart. This is like the biography of a material. It's the story it tells about its own strength, its limits, and yeah, its breaking point. I mean, think about it. How are we so confident that a massive bridge will hold up traffic, or that a simple paperclip will bend just the way we want it to? Is it all just a big, educated guess?
No way. Engineers don't guess, they listen. They have this incredibly powerful tool that lets them hear exactly what a material is capable of and how it's going to act under pressure. And that tool is the stress strain diagram.
Now, to read this story, we first have to learn the language. And it really all comes down to two key words, stress and strain. So let's break them down.
So first up, we've got stress. Now, when you pull on a rubber band, the stress isn't the pull you're feeling. It's the force happening inside the material fighting back against you, spread all across its internal structure. It's that material's inner battle to hold itself together. And what happens because of that stress? Well, that's strain. It's how much the thing actually stretches or deforms. But here's the key part. It's a ratio. It's the change in its length divided by its original length. That way, we can fairly compare the stretchiness of, say, a tiny wire and a massive steel beam. Okay, you're going to see formulas like these, but don't let your eyes glaze over. Seriously. All they're doing is putting a number on that physical story we just talked about. That internal struggle, stress, versus the physical change, strain. That's it. So now that we have the language down, we can follow the plot of this story. We're going to trace the life of a material from the moment a load is first applied all the way to the very end, when it breaks. And this right here, this is our map for that journey. You see the vertical axis? That's stress, the internal fight. And along the horizontal axis, we've got strain, the outward stretch. Every single point on this curve represents a specific moment in that material's life as it's being pulled apart. We can break this whole story down into 5 main chapters. It's a real drama. Let's walk through them one by one. Every story starts here, in the elastic region. See that straight line at the very beginning? This is the material's comfort zone. In this chapter, if you let go of the load, it snaps right back to its original shape. No problem. Just like a perfectly good rubber band. The damage is 0, totally temporary. But then, we hit a huge plot twist. It's called the yield point. This is the exact moment the story changes forever. It is the literal point of no return. Any stretching that happens after this moment is permanent. The material will never be the same again. So after that yield point, we're in what's called the plastic region. And something kind of weird happens here. It's called strain hardening. As the material deforms, its internal structure actually realigns and gets stronger. It's like it's saying, what doesn't kill me makes me stronger. But that can't last forever. Eventually, all that stretching concentrates on one little weak spot. That's called necking. And well, that's the beginning of the end. So you see, by reading this story from beginning to end, we're not just watching something break. We're actually learning about the material's true character, its built-in properties that every engineer absolutely has to know. This table is awesome because it translates all that graph speak into real-world questions. That steepness of the first straight line, that's its stiffness, which answers, how much is this going to bend? The yield point we just talked about, that's the safe load limit. It tells you exactly when permanent damage starts. The very top of the curve, that's its ultimate strength, the absolute most it can possibly handle. And the total area under the whole curve, that's a measure of its toughness. Basically, how much of a beating can it take before it finally gives up? Now here's the thing. Not all materials tell the same story. Some give you a ton of warning before they fail, while others, they just snap. This gives us 2 very different character types, ductile materials and brittle materials. And this slide just shows the difference so perfectly. Look at the ductile material. See how much it stretches out horizontally? That long, drawn-out section is the warning sign. It's screaming, hey, I'm about to fail. Now, look at the brittle material. The line goes up, and then, poof, it just ends. Almost no warning at all. It's a very short, very sudden story. So here's the bottom line. Ductile materials, like steel, stretch a lot. They give you visible signs like that necking we talked about, that things are about to go wrong. Brittle materials, like glass or a piece of chalk, fail without any heads up.
Now you can probably guess why engineers usually prefer material that screams a little before it completely breaks. Okay, let's bring this all home. Why does reading this story matter so much? It matters because understanding it is how we build a safe, reliable world around us.
Engineers live and breathe these diagrams. They use them to pick the perfect material for the job, matching its story to what a part needs to do. They design buildings and planes to make sure the real-world stresses never push the material past its yield point. And when something does break, this diagram is like the black box flight recorder. It helps them read the story of what went wrong. And hey, let me give you a couple of pro tips. Things people get wrong all the time. First, stiffness is not the same as strength. A stiff material that doesn't bend easily isn't necessarily a strong one. They're two different things. And always remember, the safe limit, that yield strength, is what designers really care about, not the absolute maximum strength it can take.
Now, I gotta be honest. This one single curve is a bit of a simplification. The story can change, sometimes dramatically, depending on things like temperature, how fast you pull on it, or if there are tiny hidden flaws already inside. So this is really a snapshot taken under perfect lab conditions.
So the next time you bend a paperclip, walk across a bridge, or use pretty much anything, think about that incredible internal battle happening inside the material. Think about its story and how engineers have learned to read it to keep us all safe. Just look around you. What stories are the materials in your world just waiting to tell?